A large language model does exactly one thing. Given some text, it predicts the next word. That's it. That is the entire trick. It doesn't look anything up. It doesn't reason in the way you or I might picture. It just guesses what comes next, one word at a time. And yet from that single, almost laughably simple ability comes all of this. It writes working code. It explains quantum physics to a 10-year-old. It holds a conversation, translates languages, drafts your emails. So the real question, the one this whole video is about, is this. How on earth does predicting the next word turn into all of that? Now, if you've seen my video on agentic AI system design, we mapped out that entire system there. And right at the center of that map sat one box, labeled the language model core. We called it the part that predicts the next word, and then we treated it as a sealed box and built everything else around it. Today, we open that box. If you haven't seen that agentic AI video, it's the perfect companion to this one, and it's linked in the description. But don't worry, you can follow everything here on its own. So let's take a single sentence and trace its journey through the machine from the words you type to the word it predicts. How large language models actually work inside the box. Part 1, turning words into numbers. Here is the first thing to understand. Deep down, a language model is a giant mathematical function, and a mathematical function cannot read the word cat. It only understands numbers, so before anything else can happen, our text has to be converted into numbers. The first step is called tokenization, and it means chopping the text into pieces. Sometimes a token is a whole word like the or cat, but longer or rarer words get broken into chunks. Unbelievable might split into un, believe, and able. Even spaces and punctuation become tokens. The model doesn't see a flowing sentence. It sees a sequence of these little pieces. And every possible token lives in a fixed vocabulary, a dictionary of maybe 50,000 or 100,000 entries. Each one is assigned a plain ID number, so the word cat might just be token number 4207. Our sentence has now become a list of numbers. Not meaningful numbers yet, just labels, but it's a start the machine can work with. You might wonder why break words into pieces at all. Why not just give every whole word its own number? There are two good reasons. First, language never sits still. New words, names, slang, and typos appear constantly, and word pieces let the model spell out anything it has never seen before by combining familiar chunks. And second, it's efficient. A vocabulary of common pieces can cover almost any text with a manageable dictionary. Tokens are the sweet spot between letters, which are too fine-grained, and whole words, which are simply too many. This one design choice explains a famously silly failure. Ask a model how many R's are in the word strawberry, and it may confidently get it wrong. Why? Because it never sees the letters S, T, R, A, W. It sees a couple of tokens, like straw and berry. It's being asked to count letters it was never actually shown. Once you know about tokens, the mistake stops being mysterious. So the first stage of our pipeline is set, text converted into a sequence of tokens. Now we need to give those tokens something they're still completely missing, meaning. Part 2, giving numbers meaning. Right now, the token for cat is just the number 4207, and that number is arbitrary. It tells the model nothing about what a cat is. The number for dog might be 19,000, and nothing about those two labels says these things are related. So each token ID is converted one more time into something richer, an embedding. An embedding is a long list of numbers, often hundreds or thousands of them. You can think of that list as coordinates, a set of directions that place the word at a specific point in a vast, high-dimensional space. A space of meaning. And here's the beautiful part. In that space, words with similar meanings end up close together. Cat and dog sit near each other, in a neighborhood of pets and animals. Paris and Tokyo cluster in a region of cities. Anger and joy live over in a district of emotions. The model learns to arrange language so that distance means similarity. It goes further than proximity. Directions in this space carry meaning too. There is, famously, a direction that roughly means royalty and another that means gender. So if you take the point for king, subtract the direction for man, and add the direction for woman, you land astonishingly close to queen. The model has captured a relationship as pure geometry, meaning turned into shape. And because meaning lives in geometry, you can literally navigate it. Start at the point for Japan, travel in the direction that means capital city, and you arrive at Tokyo. Take that very same step starting from France and you land on Paris. The model isn't looking any of this up in a table. The relationship country to capital is baked into the shape of the space itself. And there are thousands of these relationships, all encoded as directions you can travel. So now our tokens are no longer bare labels. Each one is a rich point in meaning space, but there is still one enormous problem left to solve, and it's the problem that makes these models truly powerful. Part 3, the context problem. So far, every token gets the same embedding every time. The word bank always starts as the exact same point in space, but look at these two sentences. I sat on the river bank, and I deposited cash at the bank. Same word, completely different meanings. One is a muddy riverside, the other is a financial institution. A single fixed embedding cannot possibly be right for both. The meaning of bank depends entirely on the words around it, on its context. And this is not some rare edge case, it is everywhere in language. Time can mean a clock, a magazine, or how long something takes. Spring is a season, a metal coil, or a sudden jump. Light can be a lamp or the opposite of heavy. Almost every interesting word shifts its meaning depending on its neighbors. A model that couldn't handle that would be nearly useless. So solving this isn't a nice to have, it is the whole ballgame. So what the model needs is a way for each word to look around at its neighbors and update its own meaning based on what it finds. The word bank needs to notice river sitting nearby and shift its meaning accordingly. This single idea, letting words influence each other, is the heart of the whole machine, and it has a name. Part 4, attention. This is the idea that changed everything, the breakthrough that made modern AI possible, and the core of it is surprisingly intuitive. Attention lets every word in the sentence look at every other word and decide which ones actually matter for understanding it. Take this sentence, the animal didn't cross the street because it was too tired. Now, what does it refer to? You know instantly. The animal, not the street, but nothing in the word it says so. The model figures it out through attention. When it processes the word it looks back across the sentence and pays strong attention to animal and weak attention to street. That link is how it resolves the meaning. Under the hood, each word does three things. It sends out a query, essentially asking, who here is relevant to me? Every other word offers a key, advertising what it has to offer. The query and keys are compared, and the best matches win. Then those matching words hand over their value, their actual content. It's a bit like every word calling out a question, and then listening hardest to the most useful answers. And crucially, the word then updates itself, blending in meaning from whatever it paid attention to. Our word bank reaches out, notices river is highly relevant, pulls in that context and becomes riverbank in meaning. The token didn't change. But its representation, its point in space, just shifted to fit the sentence. And every word does this all at once in parallel. But the model doesn't just look one way. It runs many attention operations side by side, called heads, and each one learns to track a different kind of relationship. One head might follow grammar, linking each verb to its subject. Another might track which pronoun points to which name. Another might just follow the overall topic. Picture dozens of these heads, all reading the same sentence through different lenses at the same time, then pooling what they each discovered. That's why you'll often hear it called multi-head attention. And the real magic is how far it can reach. Consider the sentence, the keys that I left on the kitchen counter this morning are still there. The word has to agree with keys, not counter, not morning. Attention lets her reach all the way back across the sentence, past every distraction, and lock onto keys. No simple rule about word order could get this right every time. Attention learns to connect the words that belong together, however far apart they sit. That is attention, words reading each other and adjusting. It's the engine room of the entire model, but one pass of attention only captures fairly simple relationships. To get real understanding, we do something clever. We do it again and again. Part 5, depth. A single round of attention can catch that it refers to the animal, but real language is layered. Grammar, then meaning, then tone, then intent. To capture all of that, the model stacks attention into many layers, one on top of another, dozens of them. In the largest models, well over 100. The tokens flow upward through this stack, and at each layer they get another chance to look around and refine themselves. The output of one layer becomes the input to the next, a little richer, a little more context-aware, every step of the way. And something remarkable emerges from the depth. The early layers tend to handle the simple stuff, spelling, grammar, which word attaches to which. The middle layers start assembling meaning and facts, and the deepest layers capture the truly abstract things, tone, intent, the gist of an argument. Understanding built up in stages, one layer at a time. This stack of attention layers has a name you have almost certainly heard, the transformer. It's the T in GPT. When people talk about the architecture behind modern AI, this is it. A tower of attention, turning a plain list of word points into a deep understanding of what the text actually means. And the scale here is hard to overstate. A large model might stack 90, 100 or more of these layers, and across all of them, hold hundreds of billions of those adjustable numbers. When you hear a model described as having, say, 70 billion parameters, that figure is counting the dials packed into this tower. More layers and more parameters generally means more room to capture subtle patterns, at the price of enormous computing power. So our pipeline now has real depth, tokens, embeddings, and a tall stack of attention refining meaning, which leaves the final step, turning all of that understanding back into a single next word. Part 6, making the prediction. After the text has climbed all the way through that stack of attention layers, the model has built up a deep, context-rich understanding of everything so far. Now it has to do the one job it exists for, predict the next token. It does this by producing a score for every single token in its vocabulary, all 50,000 or more, and turning those scores into probabilities. Take the sentence, "The cat sat on the." The model might output mat 60%, floor 12%, couch 8%, roof 3%. And a long tail of unlikely options after that. It's not certain, it's a ranked list of guesses. Then it picks one, and how it picks is controlled by a setting called temperature. Turn the temperature low and it almost always takes the top choice. Safe, focused, a little repetitive. Turn it up and it starts taking chances on less likely words. More surprising, more creative, and occasionally a bit unhinged. This one dial is the difference between a careful technical answer and a wild burst of poetry. And here's the final piece. Whatever word it picks gets added to the end of the text. Then the whole process runs again from the top to predict the word after that, and again, and again. Token by token, the response you read is built. That fluent flowing paragraph is really thousands of next word predictions, snapped together, one at a time. This also explains why you can ask the exact same question twice and get two genuinely different answers, because at each step the model is sampling from probabilities, not reciting a fixed script. There's a little roll of the dice built into every single word. Part 7, how it learned. We've now traced the whole path, text to tokens to embeddings up through attention to a prediction, but this raises the obvious question. Where did all of it come from? Those embeddings, those attention patterns, are really just billions of numbers called parameters. So who set them? Nobody set them by hand. The model learned them by playing one simple game at an unimaginable scale. Take a huge slice of the internet. Books, articles, code, conversations. Hide the next word and ask the model to guess it. Then compare its guess to the real word. When it's wrong, nudge every one of those billions of parameters, just slightly, in the direction that would have made the answer a little better. Now do that not once but trillions of times across trillions of words. Each tiny correction is almost nothing on its own, but repeated at that scale, the parameters slowly organize themselves. The embedding space arranges into meaning. The attention patterns learn grammar and facts and reasoning. Nobody programmed those abilities in. They emerged from relentless practice at a single game. Guess the next word. It helps to sit with the sheer size of this. The training text can run into the trillions of words, a large fraction of the public internet, plus books, code, and reference works, and the computing power is staggering. Thousands of specialized chips running together for weeks or months, consuming millions of dollars of electricity. All of that effort poured into playing one game, guess the next word, until the parameters finally settle into something that behaves as if it understands language. And one of the most surprising discoveries is what happens as these models grow. Certain abilities don't improve smoothly and gradually. They appear suddenly once a model crosses a certain size. A smaller model simply cannot do a piece of arithmetic or follow a multi-step instruction. And then past some threshold of scale it can. Researchers call these emergent abilities, skills that nobody explicitly trained which surface on their own once there are enough parameters and enough data. It's a big part of why the field has chased scale so relentlessly. But a raw model trained this way is a strange creature. It's a brilliant autocomplete that will happily continue your text in any direction, helpful or not. To turn it into an assistant, it goes through a second phase. It's shown examples of good, helpful answers and given human feedback, thumbs up, thumbs down on its responses. It's gently steered toward being useful, honest, and safe. That polishing is what turns a raw predictor into the helpful assistant you actually talk to. And if you saw the agentic AI video, this is exactly where those instructions, the system prompt we talked about, plug in. The trained model is the raw engine. The instructions and the tuning are how we point that engine at the specific job we actually want done. Part 8, what this finally explains. Once you understand the machine, its strangest quirks suddenly make perfect sense. They stop being bugs and start being direct consequences of how the thing actually works. Take hallucinations when a model states something false with total confidence. Now you know why. It was never trained to retrieve verified facts. It was trained to produce the most plausible next word. Usually, plausible and true line up nicely. But when they don't, it will state a convincing falsehood just as smoothly as the truth, because to the model, they look almost the same. It explains the context window too, that limit on how much the model can consider at once. Attention works by having every word look at every other word. Double the text and you roughly quadruple the work. That cost is exactly why there's a ceiling on how much you can feed it before it slows to a crawl or forgets the beginning. It also explains why a model doesn't know about last week. Its parameters were frozen at the end of training, like a photograph of the world on a particular date. Anything that happened afterward simply isn't in there. And that is exactly why models get connected to live tools and fresh documents, the retrieval we covered in the agentic AI video, to bridge the gap between what they learned once and what is true today. And that confident tone, even when it's wrong, the model has no built-in sense of its own certainty. It generates the words a confident expert would use, because those are the words that tend to follow this kind of question in its training data. Fluency is not the same as knowing. And it is crucial to always remember the difference. Even our strawberry problem comes right back around. It can't reliably count the letters in a word because it never saw letters, it saw tokens. Every one of these quirks traces straight back to a design choice we watched get made earlier in this very pipeline. So let's put the whole machine back together. Your text comes in and is split into tokens. Each token becomes an embedding, a point in a space of meaning. Those points flow up through a tall stack of attention layers, where every word reads every other word and refines what it means. At the top, the model produces probabilities for the next token, rolls the dice, and picks one. Then it does the whole thing again for the next word, and all of it runs on billions of parameters, shaped by one endless game of guess the next word. And that finally is what was hiding inside the box. Remember the language model core, that single sealed square from our agentic AI diagram. This entire pipeline, all of it, is what lives inside that one square, the box you have been trusting to power your agents. Now you know exactly what's in it. And here's the thought I'd love you to carry away from this. There's no little person inside, no hidden database of facts being looked up. There's a breathtakingly large pattern matcher, turning your text into geometry, letting words reshape one another, and guessing forward one token at a time. That something built on so simple a rule can write and reason and hold a conversation at all is genuinely one of the most surprising results in the history of computing. A simple rule, a staggering scale, and remarkable behavior on the other side. If this made large language models finally click for you, do me a quick favor. Give this video a like. It genuinely helps more curious people find it. And subscribe so you don't miss what's coming next, because we are building AI up from the ground, one blueprint at a time. And if you want to see how this core becomes a full, goal-driven agent, My video on agentic AI system design is the perfect next watch. It's right here. Thanks for looking inside the box with me. I'll see you in the next one.